6.1, graphing linear inequalities in two variables. So as of now, you should have finished your worksheet where you were graphing linear equations from last semester with your slope y equals mx plus b. We're still going to be using that form here in inequalities, except we're going to be highlighting parts that they don't include. So if it's just greater than this value or less than a value or equal to a value, we're going to be learning out which side of that graph that we just drew are we actually going to be shading in, what values satisfy our equation. So here it says look at the graph of y equals x. You want to actually graph that. So y equals x is y equals 1 over 1x plus 0 technically, where we have a slope of 1 and a y-intercept at 0. So we want to plot that on our graph. Y-intercept is 0. Y equals x is also whenever x is 1, y is 1. If x is 2, y is 2. So we know right now that it's going to be, if I'm going up 1 over 1, x is 1, y is 1, x is 2, and it's going to be increasing 5 and 5, 6 and 6 in a straight line like this. Negative. So connect again, your straight edge will make a much straighter line than mine did. But we see that our graph has a slope of 1 and a y-intercept of 0 there. The line divides the plane into two half planes. So we can see values on the right and the left of this line now. And this is what we're going to be really focusing on in chapter 6. So this first point, y is less than x, is in the region below the line. So y is less than x on this side of the line. If we want to shade that in. On this side of the line, whatever our x value is, our y is going to be less than it. So that's for this whole area here. On the other side of our line, we have y is greater than x. So for any x value we have, the x value will be less than our y value here. And just changing our color for highlighting, that's on this side of our line. So any value that exists here, if I ever say where y is greater than x, it's going to be above your line. If I ever say where is your y less than your x, it's going to be below that line in the blue. The line that we actually graphed, y equals x, is called our boundary line, so that's a new term for you. If my line is solid, which it is, how I graphed it, it was solid. So the solid boundary line is used to represent if I say something is less than or equal to or greater than or equal to, or I have this line underneath of my less than or greater than sign. If it was dotted, and so what I mean by dotted just in another color here, is if I were to still have the same line, but I would have had a broken line or a dotted line, that would mean that I only have less than or greater than. Nothing's equal to. So if I asked you to graph y is greater than 2x minus 1, you would graph the line like mx plus b, but then you would have a dotted line there. You wouldn't have a solid line because my sign here is no longer equals and it's only greater than. If I had y is less than or equal to 3x minus or plus 5, say, then I would want a solid line. So depending, you graph it the same way using your slope point form, so slope intercept form, your 3 is your m slope and 5 is your y-intercept. And then depending on whether or not we have an equal sign here underneath our inequality, depends on whether or not our line will be solid on our graph. To graph an inequality, we need to follow 3 steps. So we first want to graph our boundary line, which we talked about above, graphing it using our slope intercept form, y equals mx plus b. But we won't have an equal sign here in terms of the actual line. We're going to have an inequality, possibly equals as well, so less than or equal to or greater than or equal to. But we need to check out that sign first before we decide if we're drawing a solid line or a dotted line. Second step, we're going to pick a point that's not on that line and substitute it into the inequality. So for instance, if I look back at this graph up here, a point that's not on that line would be something like 2 and 0, where x is 2 and your y value is 0. That does not exist on the line, so that would be a possible testing point. If the inequality is satisfied with that point in there, I want to shade the region where that point exists. So if 2 and 0 satisfied my example, I would shade on the side of my graph in that blue area where that point exists. If that point 2 and 0 did not satisfy that equation or my inequality, then I would shade the other side. So we only have to pick one testing point. If it works, we shade the side where that point was. If it doesn't work, we know to shade the other side. Only one half plane of our graph will be shaded at a time. So let's try an example together here. We know first we want y equals mx plus b form, and this equation, this inequality, is not in that form. So I want to get y by itself and on the left-hand side. So we have 4x minus 5y is less than 20. I'm going to subtract 4x to both sides, so I now have negative 5y is less than 20 minus 4x. There is a rule that when you divide by a negative, you have to change your sign. So if I'm going to divide everything by negative 5 here, I have to actually switch my inequality to be the opposite way. So I'll have y is now greater than negative 4 plus 4 over 5x. So reminder to yourself, if you divide by a negative, you must flip your inequality. Even if there's an equal sign attached, the equal still stays. It's just if it's a less than, it's going to be a greater than. If it's a greater than, it'll switch to a less than. So just rewriting our equation so that we have it in the correct form. 4 over 5 is our slope, minus 4 is our y-intercept. We now have our graph as y is greater than 4 over 5x minus 4. Our slope is 4 over 5, our y-intercept is negative. So let's try to graph this. I know that my y-intercept is negative 4, so I have 1, 2, 3, negative 4 here. I'm going to go up 4 over 5 right here, and I know I need to connect those points. What I need to look for first is, am I going to draw a solid line between those points, or am I going to draw a dotted line? So our inequality does not have an equal sign, which means dotted. So I'm going to connect those dots with a dashed line like so. We still have arrows on the end of our line because we know it's continuous, but it's not solid because our inequality does not have an equal to. Now for shading, we want to pick that testing point. So an easy one is always 0 and 0. If it's not on the line, a go-to point would always be 0 and 0. That point's not on my line, so I'm going to plug 0 and 0 in for my x and y in this equation to see if it satisfies. So I'll do that in another color. My y is 0. Is 0 greater than 4 over 5 times 0 minus 4? Anything times 0 here is going to be 0, so 0 greater than 0 minus 4 is 0 greater than negative 4. Yes, this testing point satisfies. So our last step is, if it satisfies, we need to shade the side of our line where that point exists. So I would grab my highlighter, and I want to shade the side of my whole side of my graph where that point exists. I'm not including that line because it wasn't an equal to, but it's everything on that side of the graph where our testing point satisfied our inequality. Shading it all in, you'll just do this really neatly with a pencil or a highlighter, whatever works best for you. Remember, if you make a mistake though, you cannot erase your highlighter. So pick something that will be easy for you to work with. Example 2, graph 2x minus 5y is greater than or equal to 10. So again, we need to, our goal is y equals mx plus b. So I'm going to subtract 2x from both sides of this equation so that I can get my y by itself. If I divide by a negative, I need to switch my inequality. So I now have y is less than or equal to negative 2 plus 2 over 5 x. And switching my order so that I can see my mx plus b, I have this equation. Y is less than or equal to 2 over 5x minus 2. So let's plot our y-intercept as negative 2. I'm going to go up 2 over 5. Now I need to decide again, looking at our inequality, am I going to draw a solid line through these points or a dotted line? And I have an equal sign in my inequality, so that is solid. Solid straight line through those points with arrows on the end. Now which side of that line will I be shading? Which side satisfies? So again, pick a testing point, and 0 and 0 is not on our line, so let's start there. When I plug 0 in for my values, is 0 less than or equal to 2 over 5 times 0 minus 2? Again, that'll be 0. So is 0 less than or equal to negative 2? No, that is false. So where 0 and 0 is not the side that I want to shade. I want to shade the other shade when it does not satisfy. So because 0 and 0 didn't work, no value on that side will work. So I know to shade the other side where that point does not exist. Example 3 says graph the solution set for each linear inequality on a Cartesian plane, which is just the graphs. This is our Cartesian plane, the graphs that we've been used to working with. So we have a set, now a solution set, that's what our curly brackets tell us. For any xy point is what this is saying, where the graph is x minus 3 is greater than 0. X is any real number, and y is any real number. So real numbers are everything. That encompasses anything that we're going to be talking about on our graph so far. That includes fractions, positives, and negatives. So in order to graph this, let's get our x by itself to find our line. So add 3 to both sides. We want to graph where our x is greater than 3. So our 3, 1, 2, 3, our point is here. When I have an x equals something, that's a vertical line. It's just going to go through our x value. Now solid or dotted, we look at our inequality. There's no equals there. So I'm going to have a dotted line going through x equals 3. And then I want to shade the values that are greater than 3. So we know that without having to do a test point, that will be on the right-hand side. So with our highlighter, I would shade the x values that are greater than 3. These will be all the values in our solution set stated above. Just to confirm, you can try 0 and 0 again as a testing point. So if your x is 0, I'm plugging in, is 0 greater than 3? No, that's false. So that's why I shaded. Another reason to show why we shaded on the right-hand side, because that side of the line does not satisfy our inequality. Part B says our solution set again at any point xy, where our inequality is negative 3y plus 9 is greater than or equal to negative 3 plus y. Where now x and y are elements of integers. So integers are not fractions. They're not decimals. They're only the whole numbers that are positive and negative. So we're talking about just 1, 2, 3, 4, 5, or just negative 1, negative 2, negative 3, negative 4, not negative 2.7 or something like that. So integers we're going to show you how to represent when you have an integer versus a real number. We're going to be dotting the points in that area. Or your textbook uses the term stippled, where we'll be putting points, actual polka dots. It'll look like on the points 1 and 1, for instance. So you'll see that in a couple seconds. So let's get this into the form with y by itself on one side. So I want to get all the y's. I have a y on this side and this side. So let's bring those together. So subtract y from both sides. I have a negative 4y. And subtract a 9 onto this side is greater than or equal to negative 12. I'm dividing by a negative, so I need to switch my inequality sign. So y is less than or equal to 3. When I have just a y equals, I know I have a slope of 0, which is this represents I'm going to have a horizontal line. It's going to be going right through y is 3. So I'll plug my point here. Now, is this going to be dotted or solid? My inequality has an equal sign, so I want to have a solid line going through y equals 3 with arrows on the end of my line. And now I need to identify where am I shading. So it's less than or equal to 3, which is going to be underneath that line, right? Any y value that's less than 3 will be below that. So I want to be shading everything that's underneath that line. Now how I do this, if it's not everything, it's really not going to be the point in this box, because that's going to be, say, where x is negative 3.5 and y is 2.5. That would exist there, but that's not what an integer is, so we can't highlight everything. Now is where we stipple or we put dots on those values. So it's a little bit time consuming, but our integers are only the points where numbers meet another number on our grid. So we have to sit there, instead of shading, we stipple and put dots for integers, because that is not including all those points in between, no fractions or decimals, only positive and negative numbers. So I skipped ahead there, so you're going to have to watch me do that. So your points are stippled again because we don't include our fractions. So you want to watch your domain restrictions there on a quiz or a test, or even in your practice. Am I including all numbers, all real numbers, so is that everything and I just shade everything? Or am I limited to integers? I could possibly be limited to whole numbers, which we talked about last year is just greater than 0. We don't include any negatives there. Natural numbers is everything above 0, so 1 and up. Whole numbers are 0 and up, and integers are where we start to include our negatives and our positives. Then our rationals allow us to include our decimals and our fractions. Reals encompass all of that. So just watch the symbol for what your points are elements of.